Welcome back to the Talking Ketamine podcast. This is episode 68, Ketamine and Sleep.
Did you know that people suffering from treatment-resistant depression actually have a broken internal thermostat for deep restorative sleep? A groundbreaking new study shows that a single infusion of ketamine can specifically boost slow-wave sleep during the very first sleep cycle of the night. This research suggests that ketamine's rapid antidepressant effects might be directly linked to how it repairs and restores the brain's sleep engine.
If you are listening to this right now and, you've ever dealt with severe treatment-resistant depression, TRD, you already know the specific type of exhaustion we were talking about.
Oh, absolutely. It's intense.
Right. It's that bone-deep, just pervasive fatigue where no amount of time in bed seems to cure it. Like you wake up feeling like you literally ran a marathon in your sleep.
Yeah, it's not just feeling sleepy. It's a fundamental drain.
Exactly. And for a long time, the medical world often viewed that exhaustion as just a secondary symptom, I guess, just a byproduct of having a mood disorder. But looking at the stack of sources we have on the table today, which includes a really landmark National Institutes of Health clinical trial, plus some neurobiology papers on sleep architecture, our mission today is to explore the actual biological reality behind that exhaustion.
Because it's very real physically, not just mentally.
Yes, and we are going to examine how ketamine doesn't just put a chemical band-aid over depressive symptoms, it actually physically repairs the brain's sleep architecture so it allows for that vital overnight recovery that your brain has basically been starving for.
And to understand the sheer magnitude of this physical repair, we really first need to look at the mechanics of why a depressed brain feels so fundamentally drained in the first place.
Right, let's start there. What is happening under the hood?
Well, in neurobiology, sleep isn't just a state of resting,
Yeah.
It's this highly active, demanding physiological process. And it's governed largely by what's called the two-process model.
Okay, two-process model.
Yeah. So the first process is the circadian rhythm. Most people know this one. It's your biological clock dictating daytime wakefulness and nighttime sleepiness, mostly based on light exposure.
Sunlight, blue light from phones, that kind of thing.
Exactly. But the second process, which is called process S, that is the real focal point of this NIH research. Process S is your homeostatic sleep drive.
And I want to focus heavily on process S here because reading through the literature in our stack, it's very clear that this isn't just some metaphorical drive. It is a literal neurochemical buildup in your brain.
Yes, literal chemicals.
Right. So throughout the day, as you stay awake, your brain is accumulating this chemical called adenosine. And simultaneously, it's strengthening the connections between your neurons as you learn things and just interact with the world.
Yeah, and that strengthening of the synapses is obviously crucial, but it creates immense metabolic pressure.
It's exhausting for the brain.
Totally. The technical term for managing that pressure is the synaptic homeostasis hypothesis. So when you are awake, your synapses are firing, they're building new pathways, and getting functionally louder, if that makes sense.
Like turning up the volume on a stereo?
Right. But synaptic strength cannot just increase indefinitely. If it did, the brain would consume unsustainable amounts of energy. There'd be literally no physical space or metabolic resources left to process anything new.
It would just max out.
Exactly. The brain would essentially hit a state of maximum saturation. It would be entirely overwhelmed by its own background noise.
Which brings up the crucial mechanism of what sleep is actually supposed to do to fix that. I like to think of it like plugging your smartphone in all night. But imagine the software managing the battery is corrupted, so it only ever charges to like 10%.
That is the worst feeling.
It is. You are running on empty from the exact moment you wake up. The hardware is physically plugged into the wall, but those background apps are draining the system way faster than it can charge.
That analogy actually maps perfectly onto the electrical activity of the brain. So during the deepest phase of non-rapid eye movement sleep, the brain performs this really vital maintenance routine. It's called synaptic downscaling.
Synaptic downscaling. What exactly is getting scaled down?
Basically, it physically scales back the vast majority of those synaptic connections you built up during the day. It preserves the vital signals like your core memories and essential learning, but it ruthlessly turns down the volume on the rest of the noise.
So it's clearing out the cache, essentially.
Yeah, exactly like clearing the cache. This resetting process is what restores your brain to a baseline level, freeing up the metabolic space you need to function the next day. And the electrical signature of this entire operation, you can measure it, is called slow wave activity, or SWA.
Right, and SWA is what we actually see when we hook someone up to an EEG monitor, right? Like the brain waves visibly slow down and become these massive, synchronized, sweeping oscillations on the screen.
Yeah, they're huge waves compared to waking brain activity.
But the core tragedy of treatment-resistant depression, as highlighted in this NIH study, is that this specific homeostatic process is severely malfunctioning. Patients with TRD are just failing to build up and release that necessary sleep pressure,
Their internal thermostat for that synaptic downscaling is entirely broken.
which results in a chronic, devastating deficit in slow-wave activity. So if that internal software is corrupted, like my analogy suggests, how do we prove it? I mean, proving it requires far more than just self-reported fatigue on some questionnaire, right?
Oh, for sure. We need to actually see the engine failing in real time on a monitor. And that is why the methodology of this NIH clinical trial was so incredibly rigorous.
They didn't mess around.
No, they didn't. They conducted an inpatient monitoring study involving 91 unmedicated patients suffering from treatment-resistant depression. And that spanned both major depressive disorder and bipolar depression.
And they compared them against a control group, right?
Yeah, they compared their brainwave activity against 42 healthy volunteers.
And looking at the parameters of the study, the researchers didn't just hook them up to an EEG for a quick afternoon nap. They required 4 full nights in a specialized sleep lab using polysomnography.
Which is intense. That means full wiring, tracking everything.
Yeah, and they factored in an adaptation night first, which is crucial because of the first night effect.
Yeah.
Because nobody sleeps well in a strange environment with wires glued to their scalp.
No, you're hyper aware of everything.
So they needed a true, undisturbed baseline night to capture the brain's natural, unmedicated state before introducing randomized ketamine or a placebo infusion.
And the baseline data they captured before any treatment was administered is incredibly revealing. I mean, it physically proved the deficit we were talking about.
What did the numbers look like?
The data showed that TRD patients had significantly lower slow-wave activity compared to the healthy volunteers. And crucially, this deficit was most pronounced during the very first sleep cycle of the night.
Okay, I want to pause on that specific detail because the study emphasizes that first cycle a lot, which is known as NREM1. Why is that specific 90-minute window so critical? Like, why does it matter more than the rest of the night?
So think of the homeostatic sleep drive, like a tightly coiled spring.
Right.
When you finally fall asleep, that first sleep cycle is when the spring forcefully uncoils.
It snaps back.
Yes, it is the apex of sleep pressure release.
Mm-hmm.
The brain is the most desperate to offload the metabolic burden of the day right at the beginning of the night. If the brain fails to achieve deep slow-wave activity during that initial critical window, the downscaling process is fundamentally compromised for the rest of the entire night.
So the engine just never properly turns over.
Exactly.
That makes the macro-level sleep statistics from the baseline night even more staggering and honestly incredibly validating for anyone listening who fights this battle every single night.
The metrics were pretty catastrophic.
Yeah. Before any treatment, the depressed patients were logging about 380 minutes of total sleep time, compared to 411 minutes for the healthy group. And their sleep efficiency, which measures the actual time spent asleep while you're in bed, that was hovering around 84% compared to a healthy 90%.
And the sleep latency data is perhaps the most frustrating part.
Right, the time it takes to actually fall asleep. It took the TRD patients over twice as long. We were talking about 30 minutes of just lying there in the dark staring at the ceiling versus about 14 minutes for the healthy volunteers.
But getting back to the study design, capturing that specific deficit required strict behavioral controls during the day. The researchers actually implemented a mandatory no-napping rule for every single patient in the trial.
No naps at all.
None. They went so far as to have nursing staff and research fellows actively engage the patients in board games, puzzles, and art activities just to ensure they remained awake and upright throughout the entire day.
Okay, I have to push back on that methodology right there because looking at the protocol in our source stack, that sounds almost cruel. I mean, if you have a patient suffering from severe treatment-resistant depression and they are already running on a massive sleep deficit, wouldn't you want them to rest?
It definitely sounds harsh.
Yeah, forcing an exhausted, deeply depressed person to stay awake playing board games seems really counterintuitive to healing.
It absolutely sounds harsh from a purely comfort-based perspective, I agree. But from a neurobiological standpoint, it is really the only way to get valid data. We have to go back to process S, the homeostatic pressure valve.
Okay, the chemical buildup.
Right. The sleep drive builds up pressure like steam in a highly pressurized boiler. If a patient takes even a 20-minute nap during the afternoon, they are opening that pressure valve and letting the steam escape prematurely.
Oh, I see. So a nap effectively ruins the experiment because the brain arrives at nighttime without enough chemical pressure to trigger the slow wave response at all.
Precisely. That's the underlying mechanism. If the researchers allowed napping, they just wouldn't be able to measure the brain's true maximum physiological capacity for generating deep slow-wave activity when the night finally arrives.
Because they already bled off the pressure.
Exactly. They had to force the biological system to its absolute limit to confirm whether the internal thermostat was genuinely broken or if the patients were just distributing their sleep poorly throughout the 24-hour cycle. The strict protocol proved that the mechanism itself was malfunctioning.
Wow. Okay. So the baseline deficit is definitively proven. The depressed brain is starved of deep sleep and the engine is failing to turn over. So the critical next phase of the trial was to see if ketamine could act as the system reboot.
Right, the intervention phase.
The participants received an intravenous infusion of ketamine at zero point 0.5 milligrams per kilogram. And the electrophysiological data they captured that night is what transforms this from a standard clinical trial into a genuine, massive breakthrough.
The monitors basically showed that a single infusion of ketamine, and we really must emphasize not the placebo, triggered a highly significant increase in deep NREM1 slow-wave activity in the patients with treatment-resistant depression.
On the very first night.
On the very first night following the infusion, the drug physically repaired the depth and amplitude of their sleep waves immediately.
And the overall quality of their sleep followed suit right away, too. The total sleep time for these patients jumped from that baseline of 380 minutes to over 400 minutes. Their sleep efficiency improved dramatically, climbing past 87%.
Which is a huge jump for someone with TRD.
Oh, absolutely. And that brutal sleep latency, the time spent agonizing in the dark waiting for sleep to come, that dropped from 30 minutes down to under 20 minutes. It is basically taking a frozen, malfunctioning operating system and forcing a hard reboot.
That's exactly it.
It closes all the frozen background apps so the brain can finally run its overnight maintenance program.
And that analogy holds up perfectly when we compare ketamine to traditional sleep aids. Because standard sedatives, like certain benzodiazepines or prescription sleeping pills, they don't execute a system reboot.
What do they do instead?
They merely act as a chemical off switch. So they force the patient into a state of unconsciousness, but they actively suppress the generation of slow-wave activity.
Wait, so sleeping pills actually stop the deep sleep?
Yes, they create what we call junk sleep, where the eyes are closed. But the critical synaptic downscaling isn't actually happening. Ketamine operates entirely differently. It functions as a biological system administrator, clearing those rigid neural pathways and allowing the brain's natural restorative maintenance program to finally execute.
But reading through the findings, there is a massive caveat to this success story. This incredible increase in restorative deep sleep didn't happen for every TRD patient who received the infusion.
No, it didn't.
The data shows it only happens significantly in the responders.
And the distinction between responders and non-responders is really the crux of the entire study. The researchers defined a responder using the MADRS scale, which is the Montgomery-Åsberg Depression Rating Scale.
Right.
To be classified as a responder, a patient had to demonstrate a 50% or greater drop in their depression scores the day after the infusion. That is a massive clinical shift.
Taking someone from severely incapacitated to actually functional.
Exactly.
So if the ketamine successfully lifted the clinical symptoms of their depression, it simultaneously repaired the physical architecture of their sleep. But for the non-responders, the patients whose mood scores remained completely stagnant, their sleep architecture remained completely broken.
The slow-wave activity just stayed suppressed.
So the physical repair of the sleep cycle was directly tethered to the clinical relief of the depression.
And the specificity of this repair mechanism is further validated by looking at the healthy volunteer control group. Because when the healthy participants received the exact same 0.5 milligram per kilogram dose of ketamine, it had absolutely zero effect on their slow-wave activity.
Wait, it didn't push them into an even deeper state of supersleep?
Not at all. In pharmacology, we refer to this as a ceiling effect. The healthy brains were already functioning at optimal homeostatic capacity. Their synaptic downscaling processes were perfectly intact, meaning the ketamine had no structural malfunction to correct in the first place.
It only initiated a repair sequence in the brains where the system was actively failing.
Right.
This specificity brings us to a highly complex variable in the study, which is the age factor. If ketamine works by forcing this plastic structural reset, We have to ask what happens when the drug encounters a brain that has been running on corrupted software for decades.
That's a vital question.
Because the literature in our source stack notes that an older brain inherently struggles a lot more with these mechanisms.
The biological reality of aging is a critical limitation we really have to acknowledge here. As human beings naturally age, our intrinsic ability to generate high-amplitude slow-wave activity declines. Our sleep architecture naturally becomes lighter and much more fragmented.
Which is why older people tend to sleep less or wake up more often.
Precisely. And concurrently, the brain's overall ability to rewire itself, its synaptic plasticity, also diminishes.
And the trial data aligns directly with that biological reality. The researchers found a stark negative correlation regarding age. Basically, the older the TRD patient was, the less pronounced the ketamine-induced boost in deep sleep became.
And this failure to generate the restorative sleep wave was overwhelmingly prominent in the older non-responders.
To understand why an older brain fails to execute this reboot, we have to look briefly at the molecular chain reaction triggered by ketamine, right?
Yeah. When ketamine is introduced, it creates a rapid, massive surge of a neurotransmitter called glutamate. This glutamate burst acts as a catalyst, triggering the release of a crucial protein called BDNF. That's brain-derived neurotrophic factor.
Now, I often hear BDNF described in pop science simply as fertilizer for the brain. But based on the complex structural changes we are discussing today, that metaphor feels way too passive. Fertilizer just sort of sits in the dirt.
Yeah, it's not a great metaphor. A much more accurate way to visualize DDNF is as an aggressive biological construction crew.
Oh, okay, construction crew.
Yeah, so when that glutamate burst releases BDNF, this crew is deployed to physically force new structural branches, which are called dendritic spines, to sprout from the neurons. They're essentially taking jackhammers to hardened, rigid neural pathways, forcing the brain to physically rewire its connections in real time.
But I mean, even the best construction crew can't build a new skyscraper if they don't have any steel or concrete. They need raw materials to work with.
Exactly. And that raw material is what neurobiologists call plasticity reserve. The brain has to possess a certain baseline level of flexibility and cellular health to successfully execute the massive physical rewiring demanded by that overnight sleep reset.
And if they don't have it?
Well, if a patient is older and their brain has been locked in the rigid, unyielding neural pathways of severe depression for 20 or 30 years, that plasticity reserve may be severely depleted. The ketamine successfully triggers the chemical alarm, the BDNF construction crew shows up, but the brain simply lacks the structural flexibility required to actually carry out the repair.
That feels incredibly heavy for anyone listening who has been fighting this illness for decades. Does this age-related limitation mean older patients shouldn't hold out any hope for this mechanism? Or does it just mean their brains require significantly more scaffolding and support to overcome years of entrenched, rigid neural pathways before they can finally achieve that deep sleep reset?
It strongly points to the latter, and it is a crucial distinction to make. Diminished plasticity reserve absolutely does not equate to zero hope.
Okay, that's good to hear.
What the data suggests is that a single, isolated infusion of ketamine is simply insufficient to break through decades of entrenched neural rigidity. An older brain requires a vastly different, more sustained protocol.
Like what?
This might involve repeated, stacked dosing schedules, or coupling the ketamine infusions with intensive behavioral therapies designed to coax out plasticity over a much longer timeline. Think of the brain effectively as a muscle. If it has been immobilized in a cast of depressive rigidity for decades, a single physical therapy session isn't going to result in perfect flexibility.
Right, you'd need months of work.
Exactly. The system needs targeted, sustained interventions to rebuild that plasticity reserve before the overnight sleep engine can finally turn over.
Understanding the mechanics behind why the medicine works or why it sometimes requires more time is deeply empowering, and it actually sparks a fascinating thought regarding the future of psychiatric care based on these findings.
What are you thinking?
Well, we established that this profound deep sleep reset only happens in the patients whose depression actually responds to the treatment. And we established that this electrophysiological change occurs on the very first night.
Right, the very first sleep cycle even.
So rather than subjecting a patient to a new antidepressant, waiting 6 agonizing weeks, and having them fill out a subjective questionnaire to guess if they feel slightly better, what if we leverage technology?
Oh, I see where you're going with this.
Could we soon use simple medical-grade wearable sleep trackers immediately after a single treatment to predict efficacy? Imagine a smartwatch that monitors your slow wave activity overnight, and by breakfast, it transmits a data point to your doctor confirming the internal thermostat has reset, the synaptic downscaling is active, the drug is working.
The integration of electrophysiological data into standard psychiatric practice is a phenomenal proposition.
Mhm.
If subsequent trials can definitively validate that the signature of recovery occurs precisely during that first night's sleep architecture, consumer or medical-grade wearables could completely revolutionize the diagnostic timeline.
It would change everything.
It really would. It strips away the subjective guesswork of psychiatric questionnaires and provides real-time objective biological data confirming whether the brain's physical hardware is actively healing.
It's so validating to hear that the exhaustion of depression isn't just in our heads, but represents a physical sleep deficit that ketamine can help repair.
Exactly. Sleep by restoring the brain's natural deep sleep cycles. Ketamine appears to give the brain the overnight recovery time it desperately needs to heal.
A truly hopeful step forward. Thanks for listening to the Talking Ketamine podcast. We'll catch you on the next one.